Welcome to the session on Laplace transform. In the previous classes, we discussed the Laplace transform and some properties. Here we shall discuss another properties of the Laplace transform. First one is the Laplace transform of derivatives. If f dash of t is continuous and Laplace transform of f of t is equal to f of s, then the Laplace transform of f dash of t, which is equal to s into f of s minus f of 0. Here we used capital F for the transform and small f is the function f of t. This is the transform of derivative f dash of t, that is s into f of s minus f of 0. We have to show this result by the basic definition of Laplace transform. We have Laplace transform of f dash of t is equal to integral 0 to infinity e raised to minus st into f of t f dash of t dt. Here the function is f dash of t. Therefore, we multiply f dash of t by e raised to minus st and then integrate this product between the limits 0 and infinity with respect to integration with respect to t. This is equal to e raised to minus st into, we take first function as e raised to minus st and the second function as f dash of t, then integral of e raised to minus st into f dash of t dt is equal to e raised to minus st into first function into integral of the second means integral of f dash of t with respect to t, which is f of t between the limits 0 and infinity minus integral of, here derivative of first means minus s into e raised to minus st into integral of the second function, that is integral of f dash is f, that means f of t dt. The limits are 0 and infinity. This is equal to, when we apply this infinity, the upper limit infinity, this is equal to e raised to minus infinity into f of infinity minus, apply the lower limit 0, we get e raised to 0, that is 1, that is e raised to 0 into f of 0 minus, here negative of negative is plus, integral from 0 to infinity. This s can be taken outside because here the integration is with respect to t. Therefore, we get s into integral 0 to infinity e raised to minus st f of t dt. This is equal to, here this function, this value, this first term tends to 0 because f of t does not grow more than e raised to minus st. Therefore, this term tends to 0 minus this is e raised to 0 means 1 into f of 0, that is f of 0 plus s into integral from 0 to infinity e raised to minus st f of t dt is the definition of Laplace transform of f of t. That is Laplace transform of f dash of t is equal to s into Laplace transform of f of t minus f of 0. That is s into Laplace transform of f of t is f of s minus f of 0. This is the transform of derivatives. Similarly, we can prove that Laplace transform of the second derivative f double dash of t is equal to s square into f of s minus s into f of 0 minus f dash of 0. And Laplace transform of f triple dash of t, that is the third derivative of f of t, which is equal to s cube into f of s minus s square into f of 0 minus s into f dash of 0 minus f double dash at 0, and so on. In general, we can show that the Laplace transform of the nth derivative fn of t, which is equal to s raised to n into the Laplace transform of f of t minus s raised to n minus 1 into f of 0 minus s raised to n minus 2 into f dash at 0 minus etc. minus fn minus 1th derivative at 0. Here f of 0, f dash of 0, etc., the n minus 1th derivative of f at 0 should be exist, which is the condition for this expression. This is the transform of derivatives. All these derivatives should be continuous. Then we can write this property. The next property is transform of integrals. If Laplace transform of this is the property, if Laplace transform of f of t equal to f of s, then the Laplace transform of integral from 0 to t f of t dt, that is we just integrate f of t between the limits 0 and t with respect to t and take Laplace transform, which is equal to 1 by s into f of s. That is we just multiply f of s by 1 by s when we want to find the Laplace transform of this integral. Here note that the limits are 0 and t. We can prove this property. We have the definition of Laplace transform. Sorry, consider this function, this integral, that is integral 0 to t f of t dt. We name this as phi of t. Then we can write phi dash of t as if phi of t equal to integral from 0 to t f of t dt means phi dash of t is equal to f of t. And clearly when t equal to 0 we get phi of 0 as 0, phi of 0 equal to 0. Now consider the Laplace transform of phi dash of t. Here phi is a function of t, then we can find the Laplace transform of derivative of phi, which is equal to s into Laplace transform of phi of t minus phi dash of 0, sorry, phi of 0, which is from the property of transform of derivatives, that is Laplace transform of first derivative phi dash of t is equal to s into Laplace transform of phi of t minus phi of 0. Here phi of 0 is 0, therefore we get this is equal to s into Laplace transform of phi of t minus this term is 0, therefore Laplace transform of phi dash of t is equal to s into Laplace transform of phi of t. Therefore we can write Laplace transform of this phi of t as 1 by s into Laplace transform of phi dash of t. That is equal to 1 by s into Laplace transform of phi dash of t is f of t. That means Laplace transform of phi of t is equal to 1 by s into Laplace transform of f of t. That means here Laplace transform of phi of t is, or phi of t is integral from 0 to t f of t dt. That is the integral from 0 to t f of t dt is equal to 1 by s into Laplace transform of f of t is f of s. This is the property of transform of integrals. That is, in order to find the Laplace transform of integral of this form 0 to t f of t dt is, we just multiply f of s by 1 by s. Now consider this example. We know that Laplace transform of sine 2t is equal to 2 divided by s square plus 2 square, that is 4. Then Laplace transform of integral from 0 to t sine 2t dt is equal to, we have to use this property because the limits of integration are 0 and t. This is equal to 1 by s into f of s. Here f of s is this function 2 by s square plus 4, which is f of s. F of t is sine 2t. Therefore we multiply this f of t means this sine 2t, sorry, we integrate this function between the limits 0 and t means we have to multiply the transform 2 by s square plus 4 by 1 by s, that is equal to 1 by s into 2 divided by s square plus 4. We can verify this because integral from 0 to t sine 2t is integral of sine is minus cos 2t divided by 2 between the limits 0 and t. This is equal to, this minus 1 by 2 can be taken outside, into cos 2t. When we apply the upper limit t for t, then this is cos 2t itself, minus, when t equal to 0, this is cos 0 is 1, which is equal to minus 1 by 2 into cos 2t minus 1 means we can write this as 1 minus cos 2t divided by 2. Now we take the Laplace transform, we get Laplace transform of integral from 0 to t sin 2t dt is equal to 1 by 2 into Laplace transform of 1 minus cos 2t, which is equal to 1 by 2 into Laplace transform of 1 minus Laplace transform of cos 2t, which is equal to 1 by 2 into Laplace transform of 1 is 1 by s minus Laplace transform of cos 2t is s by s square plus 2 square is 4, which is equal to 1 by 2 into s into s square plus 4 in the denominator. Here s square plus 4 minus s into s is minus s square, that is s square minus s square will become 0. The remaining term is minus 4. Sorry, plus 4. 4 by 2 is 2, that is 2 by s into s square plus 4. Here we obtained by this property Laplace transform of integral from 0 to t sin 2t dt as 2 by s into s square plus 4. Therefore, we just verified this property. The next property is multiplication by t raised to n. If the Laplace transform of a function f of t is f of s, then Laplace transform of the function f of t multiplied by t raised to n, that is Laplace transform of t raised to n into f of t is equal to minus 1 raised to n into nth derivative of f of s with respect to s. That is L of t raised to n into f of t is equal to minus 1 raised to n into the nth derivative of f of s with respect to s. This is the property of multiplication by t raised to n. In particular, for n is equal to 1, Laplace transform of t into f of t is equal to minus 1 raised to 1 means minus 1 into, for n equal to 1, this will become the first derivative d by ds of f of s. That is, we just differentiate the Laplace transform of f of t with respect to s and we multiply by minus 1, which is the Laplace transform of t into f of t. That means the function f of t multiplied by t. And for n is equal to 2, L of t square into f of t is equal to minus 1 square into, For n equal to 2, this will become the second derivative, d square by ds square of f of s. For n is equal to 3, L of t cube into f of t is equal to minus 1 raised to 3 into the third derivative of f of s with respect to s, and so on. In general, L of t raised to n into f of t is equal to minus 1 raised to n into nth derivative of f of s with respect to s. This is the property of multiplication by t raised to n. Consider this example. Consider the function e raised to 2t. F of t equal to e raised to 2t. Then the Laplace transform of e raised to 2t is 1 by s minus 2. Because Laplace transform of e raised to at is 1 by s minus a, here a is equal to 2. Now, if we multiply this function with t, we get take the Laplace transform, we get Laplace transform of t into e raised to 2t, which is equal to, by this property we can write minus 1 into first derivative of f of s. Here f of s is 1 by s minus 2. Therefore, this is equal to minus 1 into d by ds of 1 by s minus 2, which is equal to derivative of 1 by s minus 2 is minus 1 by s minus 2 the whole square. Minus 1 into minus 1 divided by s minus 2 whole square means 1 by s minus 2 the whole square. That is Laplace transform of the function e raised to 2t multiplied by t is 1 by s minus 2 the whole square. We can verify this L of t into e raised to 2t is 1 by s minus 2 whole square, because we know that Laplace transform of t is equal to gamma 2 divided by s square. Gamma 2 means 2 minus 1 factorial, that is 1 by s square. L of t is equal to 1 by s square. Now, by the first shifting theorem, we can write Laplace transform of t into e raised to 2t. That is, we multiply this t by e raised to 2t, then the corresponding transform will become 1 by s minus 2 the whole square, because we just replace s by s minus 2. If we multiply a function by e raised to at, then taking the Laplace transform means we have to replace s by s minus a the whole square, which is the first shifting theorem. By first shifting theorem, we can find the Laplace transform of e raised to 2t into t, which is equal to 1 by s minus 2 the whole square. Also, we found that Laplace transform of t into e raised to 2t is 1 by s minus 2 the whole square by this property of multiplication by t. Both are same. Now, let me conclude this session. In this session, we discussed three properties. First one is the transform of derivatives, and the second is transform of integrals, and also the third one is multiplication by t raised to n. Thank you for listening this class. Have a nice day.